Hi, my name is Arjun Samavedam, and I'm a rising senior at Montgomery Blair High School. My project is Sixth Sense, a low-cost wearable AR and haptic solution for the hearing impaired. To give an overview of my project, general hearing impairment is a widespread issue, affecting hundreds of millions worldwide. My project aims to develop a low-cost device that mounts on a user's eyeglasses to provide limited speech recognition and haptic alerts to the user in order to remediate sensory loss. As I mentioned, hearing impairment affects more than 450 million people around the world. In the US alone, more than 1.2 million adults who have severe hearing impairment could benefit from cochlear implants, yet less than 10% of them do, as a result of their high cost and inattainability. With recent advancements in computationally efficient speech recognition algorithms and the utilization of augmented reality to integrate visual display in the real world, this device proposes an affordable, non-invasive hearing assistive device that integrates limited speech recognition, haptic feedback, and augmented reality in order to improve accessibility in the daily experiences of individuals who have severe hearing impairments. Overall, this device had 5 primary criteria: to consist of a compact design, to be able to be easily mounted on a user's eyeglasses, to be able to recognize speech from the environment with high accuracy and display it to the user, to reliably identify critical noises such as horns and sirens and provide haptic feedback, to achieve a battery life of at least 10 hours, and for the total component cost to come under $25. So the device you see on the right here is Sixth Sense, which aims to bridge the gap in accessibility and affordability of the current hearing impairment assistive devices issue. It mounts on a user's eyeglasses to provide all of its functionality. The device is built around multiple key components. The microcontroller is the ESP32S3, which has a small form factor and has sufficient computational power to run both of the lightweight machine learning models necessary for the device's functionality. I'll talk about those a little bit later. It also includes a MEMS microphone, which is able to obtain sufficiently clear audio data and is quite small. It also uses a 128 by 64 OLED display, which is critical for rendering recognized speech and ambient noises to the user. Additionally, it uses 2 touch sensors, which are used for user input to the device, a haptic motor, which is used for haptic feedback from ambient noises, as well as a battery. All of these components are housed by a 3D printed housing, designed to be lightweight and attached to the user's eyeglasses. You can see some CAD models on the bottom here. A key part of the housing is the optical path it creates. As you can see, text and visuals originate from the OLED display, which are then reflected by the 45-degree angled mounted mirror and are sufficiently magnified and focused by the convex lens in order to successfully render onto the plastic screen. All of this ensures that the text is focused from the user's perspective. Because the distance between the eye and the screen is so short, it's critical that this path exists. As you can see on the bottom is the actual physical prototype, and on the bottom right you can see a text rendering of what a user would see. The Sixth Sense device has an electrical circuit design that permits all of its components to work together to provide limited real-time text translation and all of its other functionality. We can see the circuit diagram on the bottom left, as well as the components laid out visually on a breadboard on the bottom right. To communicate with each of the components, the microprocessor utilizes various hardware protocols: SPI via the OLED display, I2S with the MEMS microphone, and GPIO with the haptic motor. Additionally, a 3.7 volt rechargeable battery provides the power source for the entire circuit. The software of the device implements a thread-based approach, which allows it to dynamically allocate resources to maintain performance while optimizing power consumption. The main process controller serves to continuously monitor touch sensor inputs and creates and removes threads accordingly to the user's desires. It implements a state machine consisting of 3 primary modes. The first mode is a multi-net model for speech recognition, which leverages expressives, who actually creates the ESP chips, lightweight speech recognition model. It utilizes phoneme-based recognition, which means that it uses sound syllables rather than training the model on the words itself. This allows the device to easily configure and recognize up to 200 speech commands. Once a speech command is recognized, it is mapped to its English equivalent phrase and successfully rendered to the user on its screen. The next mode is the ambient noise recognition model, which is a customly developed TinyML1D convolutional neural network audio classifier trained on horn and siren data points via the Edge Impulse platform. By using the Edge Impulse platform, I was able to generate a C++ library which is designed for efficient integration in microcontrollers such as the ESP32. When the model is active, it recognizes horns and sirens from the active microphone input and appropriately provides haptic feedback to the user, as well as displays an alert to the user on the screen. The last primary mode is the deep sleep mode, which utilizes ESP32's ultra-low power capability functions to draw just 9 microamps when it's in this state, as compared to the base 34 milliamps. Taking a look at the general device power consumption, we can see a diagram and a table on the bottom here that demonstrates the power consumption in various modes, with the models active consuming about 68 milliamp hours. This would durate the charge about 5.4 hours if it was just inside this. But with the deep sleep mode, it could last on deep sleep for about 57 months. A continuous usage of all of these different modes would easily last the device about 10 hours, probably even 20 hours in a user's day. Summing all of the component costs results in a total cost of just $18.50, which we can see on the top right table. With the prospective PCB board implementation, this would come to about $23.50, which is successfully under the criteria of $25. Taking a look at the models and their performance, we'll take a look at the speech recognition model first. It was from the total 100 phrases used to configure the model, 20 of them were randomly taken in order to perform these trials. The model is tested against these phrases at a standard conversation distance of 5 feet, with background noise levels varying from 30 decibels, which would be a quiet space, to 60 decibels, which would be an environment like a restaurant. We can see in the table the results of 2 trials demonstrating a general average success rate of about 70 to 80% accuracy across varying amounts of noise level. The model is able to maintain a relatively robust performance even with the increase in ambient noise, demonstrating general viability for usage in a range of environments. Taking a look at the performance of the ambient noise recognition model, it was tested in a range of distances and a range of background noises. As shown in the table on the bottom, it ranged from about 85 to 100% success rate. This consistency and accuracy can be attributed to the fact that noises like car horns and sirens have frequency energy that is more easy to identify consistently. This high performance indicates large amounts of viability in the model to be expanded upon further to other sounds as well. Overall, the 6th Sense device successfully is able to integrate speech recognition and ambient noise recognition with augmented reality to create a low-cost device able to be mounted successfully on a user's eyeglasses. It demonstrates how innovative engineering can create practical, cost-effective solutions to enhance real-time communication and environmental awareness for individuals with severe hearing impairments. Future work includes enhancing the speech recognition accuracy of the model, expanding the number of sounds recognized by the audio classifier, improving the charge duration, and to generally further productize the device. Here are the references utilized. Thank you.